Week 4, Introduction to Exploratory Data Mining. Welcome to Week 4. This lesson introduces you to exploratory data mining in Python. Data mining helps you discover patterns and insights from real-world data. We will use the groceries dataset to practice data pre-processing, exploratory analysis, association rules, classification, clustering, and more. By the end, you will be confident to explore, clean, and analyze new datasets yourself. Running the cell now. Ask yourself, have you ever noticed patterns in your shopping habits? Let us get our data ready to start exploring. We import the warnings module to manage warning messages. We suppress all warnings to keep the output clean and free from distraction. We import pandas, a powerful library used for data manipulation and analysis. We import KaggleHub and OS. KaggleHub helps to download datasets, and OS helps interact with the operating system. We list all files in the downloaded dataset directory. We import NumPy as NP, a library for numerical operations. We set the random C to 42 to ensure reproducible results. We find the CSV file from the downloaded files by checking the file extensions. We load the dataset from the CSV file into a pandas data frame for processing. We print the shape of the data frame to understand its dimensions, rows and columns. We print the first 3 rows to get a quick look at the data. Running the cell now. The output shows the groceries dataset has 38,765 rows and 3 columns, indicating a large number of transactions with key details, member ID, purchase date, and item description. This initial exploration helps us understand the dataset structure and scope, which is essential before digging deeper into patterns and trends in Week 4's exploratory data mining exercises. Practice: what columns can you spot in this sample? Try naming them aloud. Step 1. Understanding the dataset. Our groceries dataset contains items purchased by shoppers. Each row records a person, the shopping date, and which specific item they bought. To use this for data mining, we will group all items bought together on the same shopping trip. Let us explore what information is available. Running the cell now. When working with new data, always take time to get to know your features. Let us look at all the columns and see what data types they have. We print the data types to see if we have numbers, text, or dates. We print the column names to help understand what information we have. This gives us a quick overview of the dataset structure. Running the cell now. This output confirms our dataset has 3 key columns, a numeric member ID, a date stored as text, and an item description as text. Noticing these types helps us understand what data cleaning or conversion might be needed before analysis. It sets the foundation for exploring how individual shoppers and purchase dates relate to items bought. Try to think which columns might be useful for finding buying patterns. Missing values or gaps in data. Let us see if any cells are empty. We look for missing values in every column. This is an important step before analysis, because missing data can cause errors. Running the cell now. This output shows that there are no missing values in any columns of our groceries dataset, meaning every purchase record is complete with shopper ID, date, and item description. This check ensures the data quality is good before we begin analysis, allowing us to confidently explore patterns without worrying about gaps. Why do you think some data might be missing? Discuss with a friend or write your guess. Cleaning data helps us avoid problems later. We remove any rows that have missing values. This step ensures we only analyze complete records. We print the new shape to confirm how many rows remain. Running the cell now. After removing any rows with missing data, our dataset now contains 38,765 entries and 3 columns, person, date, and item. This confirms that our data is clean and complete, setting a solid foundation for analyzing shopping patterns accurately. Imagine you run a supermarket. Why might you want to remove incomplete records? Let us get a sense of the data size by counting unique shoppers and items. We count how many different shoppers we have. We count how many different products appear in the dataset. Knowing these numbers helps us understand the variety in the data. Running the cell now. This output shows there are 3,898 unique shoppers and 167 unique items in the dataset, highlighting its size and diversity. Noticing these counts helps us understand the scope of the data we're working with and guides how we approach analysis, such as tracking individual shopping habits or item popularity. Try guessing, which do you think will be larger, number of shoppers or number of items? Let us see the 5 dates with the most shopping entries. We list the top 5 dates when most items were bought. This can help us spot patterns, like busier shopping days. Running the cell now. This output lists the top 5 busiest shopping dates, showing how many purchases were made on each day. Notice the counts, all close to 90 or more, indicating peak shopping times within the dataset. This helps us understand temporal patterns in the data, a key step in exploring shopper behavior. Can you think of reasons why some days might be busier? Step 2. Preparing basket data. For many data mining tasks, we need to know every item bought in each shopping trip. Let us group the data by shopper and date, and collect all items into a basket. This basket format will help us discover popular item groups and rules. Running the cell now. Can you imagine the usefulness of learning what items are bought together? Grouping items into baskets is a foundational step for association analysis. Here, every basket represents what one shopper bought on one visit. We create a list of items for each shopping trip by grouping by shopper. A new column stores how many items each basket contains. We preview the result. Now, each row means a single shopping trip's basket. Running the cell now. This output shows the first 3 shoppers with their respective baskets, where all items purchased by each member are grouped into a list under item description. The new basket _size column indicates the total number of items in each shopper's basket, highlighting the variation in basket sizes. This confirms the code's intent to aggregate items per shopper, a crucial step for transaction-based analysis like market basket mining. Think of a time you bought several things at the store. What did your basket contain? Let us summarize how many items people buy per shopping trip. This shows the minimum, average, and maximum number of items in a basket. It reveals if shoppers usually buy just a few things or fill up their carts. Running the cell now. This summary describes the distribution of basket sizes, showing that the average basket contains about 10 items, with a range from 2 to 36. Notice the spread indicated by the standard deviation and quartiles, which highlights typical and larger shopping trips. This confirms that grouping by shopper and date effectively captures varied basket sizes essential for analyzing purchasing patterns. Can you guess the most common basket size before you look? Let us see which products are most popular. We look for the 10 most frequently purchased items. These top sellers can help stores decide what to keep in stock. Knowing popular products is useful for both analysis and business. Running the cell now. This output shows the top 10 most frequently purchased items in the dataset, highlighting key products like whole milk and other vegetables. Noticing these item counts helps us understand common purchase behavior, which is essential when grouping items into baskets for further analysis. This step confirms the data contains meaningful item transactions before we aggregate them by shopper and date. What would you expect to see here? Compare your guess to the results. Step 3. Discovering association rules. Association rule mining finds which items are bought together, like if milk, then bread. To do this, we build a basket matrix. Rows are baskets, columns are items, and cells show if the item was bought. We use the Melksten package and a priori algorithm. Running the cell now. Association rules are widely used for market basket analysis in retail. Let us create a useful format for mining association rules. Import the transaction encoder class from the Melksten.preprocessing module. Create a transaction encoder instance to transform baskets into a Boolean matrix format. Initialize the encoder and fit it to the item description column, then transform the data. Create a data frame from the transformed Boolean array, labeling columns by item names. Print the shape of the resulting basket matrix to see its dimensions. Print the first 3 rows of the basket matrix to inspect the output. Running the cell now. This output shows the basket matrix created from the transaction data, with 3,898 baskets, rows, and 167 unique items, columns. Notice how each cell is a true/false value, indicating whether an item was purchased in that basket. This binary format is essential for running a priori to find association rules. The wide shape and detailed item columns prepare the data for discovering patterns like fifth milk, then bread in the next steps. Try picturing a row as a shopping trip and see which items line up as true. Now we will discover some popular rules in the shopping baskets. We import the a priori algorithm and association_rules function for market basket analysis. We find frequent item sets, which are groups of items that commonly appear together in baskets. We specify a minimum support of 2%, so we only keep item sets that appear in at least 2% of all baskets. Then we generate association rules from the frequent item sets using lift as the metric, with a threshold of 1.2 to find meaningful rules. We print the first 5 rules showing their antecedents, consequence, support, confidence, and lift values. Running the cell now. Here, the output shows the top association rules discovered from the basket matrix, with key metrics like support, confidence, and lift. Notice how pairs like bottled water, UHT milk, have a lift above 1, indicating these items are purchased together more often than by chance. This confirms the a priori algorithm is successfully uncovering meaningful item relationships to inform potential product bundling or promotions. If you managed a store, how would you use these rules to boost sales? Let us plot the strongest rules to make them easier to compare. We add a comment to explain that we will visualize the top 5 rules based on confidence. We import the matplotlib.pyplot library to create plots. We select the top 5 rules with the highest confidence scores. We create a horizontal bar chart where each bar represents a rule's confidence, labeling bars with the rule's antecedent and consequent. We set the label for the x-axis to confidence. We set the title of the plot as top 5 association rules. We display the plot on the screen. Running the cell now. This bar chart displays the top 5 association rules sorted by confidence, showing the strength of each rule, from items in the antecedent leading to items in the consequent. Notice how the horizontal bars make it easy to compare confidence values, reinforcing which item combinations are most reliably brought together in the dataset. This visualization helps us quickly identify the strongest patterns found through the association rule mining step. Pause and think, which rule here might surprise you? Step 4. Basic classification setup. For machine learning, classification aims to predict a label. For practice, let us say we want to predict if a shopper will buy a whole milk or not. This is a simplified classification task we can try with the groceries data. Running the cell now. Classification is common for email spam filters, medical diagnoses, and more. Let us build our label for classification. We add a new column for our target. Did the basket include whole milk? We create the target column buys_whole_milk by copying values from whole milk. We create our feature matrix X by dropping the target column from the data. We assign the target vector Y as the buys_whole_milk column. Running the cell now. Here, we've created the target labeled buys_whole_milk by copying the whole milk column, which shows whether each shopper bought whole milk or not. We then separate the features X from the label Y to prepare for classification. This setup is essential as it clearly defines what we're trying to predict in our model. What other items do you think could be used as labels for prediction? To know if our model works, we need to test it on unseen data. We use train_test_split to split items into training and testing sets. 75% goes to training, the rest is for testing our model. We use a fixed random seed so results are reproducible. Printing the shapes helps check our split looks right. Running the cell now. Here we see the shapes of our training and testing datasets after splitting 2,923 samples for training and 975 for testing, each with 167 features. This confirms our data is properly divided, which is crucial for building a reliable classification model to predict whether a shopper will buy whole milk. Notice the consistent number of features ensures the model can learn and evaluate from the same input structure. Why is it important to test a model on data it did not see during training? Let us train a simple logistic regression model to predict whole milk purchases. We start by noting that we are training a simple logistic regression classifier. We import the logistic regression class from the sklearn.linear_model module. Next, we create an instance of logistic regression with a maximum of 200 iterations. We train the logistic regression model using the training data features and labels. Finally, we print the accuracy of the model on the test data. Running the cell now. The output shows a perfect test accuracy of 1.0, indicating the logistic regression model classified our test shoppers as buying whole milk or not with 100% accuracy. This highlights that even a simple classifier can achieve strong results on this data, reinforcing the core concept in this step, setting up a basic classification model to predict a target label. You have made your first buying behavior prediction. Step 5. Clustering with K-means. Clustering groups baskets with similar purchase patterns. This is useful for finding customer segments automatically. Let us cluster a sample using the K-means algorithm from scikit-learn. We will cluster using a smaller set of item columns for speed. Running the cell now. Clustering helps marketers and stores offer personalized products. Let us try clustering on the 10 most common items. We pick the 10 most frequent items as our features. We get the names of these top items to use as columns. We select these columns from the basket matrix to create a sample for clustering. We import the K-means clustering algorithm from scikit-learn. We create a K-means model to find 3 clusters, setting a random state for reproducibility. We apply the K-means model to assign each basket to a cluster. We add the cluster labels as a new column in the sample_basket data frame. We print the average values of each item for baskets in each cluster to understand their characteristics. Running the cell now. The output shows the average purchase frequency of the top 10 items in each of the 3 clusters identified by K-means. Notice how Cluster 0 and Cluster 2 have high values for other vegetables, but only Cluster 2 strongly buys rolls spuns, indicating distinct customer segments based on buying patterns. This helps us understand how clustering groups similar baskets to reveal meaningful customer behavior. Look at which items are more or less common in each cluster. What stands out? Step 6. Mini-project Market Basket Insights. Practice. Create your own rule or cluster analysis. Try changing the item or support threshold and see what new patterns appear. You can analyze a different top item, or use more or fewer clusters in K-means. Exploring parameters is the best way to learn. Running the cell now. Let us let you try predicting a purchase for any item you like. This comment explains that you can try predicting the purchase of another item. Prompt the user to enter the name of an item to predict, for example, soda. Check if the entered item exists as a column in the basket matrix data. If it exists, import the Logistic Regression class from scikit-learn to use for modeling. Set Y2 as the column representing purchases of the specified item. Set X2 as all other items purchase columns except the current item and buys_whole_milk, if present. Split the data into training and testing sets with 25% of data for testing and a fixed random seed. Initialize a logistic regression model, limiting iterations to 100. Train the logistic regression model on the training data. Print out the accuracy score of the model on the test data for the specified item. If the item does not exist in the columns, print a message telling the user to try again. Running the cell now. This output shows that the entered item was not found in the basket matrix columns, which means it isn't part of the dataset used for prediction. This highlights the importance of choosing valid item names when applying the logistic regression model to predict purchases. Experimenting with different valid items helps uncover new purchase patterns and improves your understanding of model accuracy in market basket analysis. Try running this cell with apples, curd, or any popular grocery item. Remember to like and subscribe for more hands-on lessons. Let us experiment with different numbers of clusters. We try cluster numbers from 2 to 5. We print each one's inertia, which is a measure of how close baskets are within clusters. Lower inertia means tighter groupings. This helps you choose the best value of K for clustering. Running the cell now. This output shows the inertia values for K means clustering with different numbers of clusters, K equals 2 to 5, where lower inertia indicates tighter, more compact clusters. Notice how inertia steadily decreases as K increases, suggesting that adding more clusters improves the fit, but with diminishing returns. This helps decide the best number of clusters to capture meaningful market basket patterns without overfitting. Notice how inertia changes with more clusters. Troubleshooting and best practices. If something does not work, check for typos and missing dependencies. Always inspect your data before trusting results. Test your logic with small samples to spot errors early. Document your process in comments and mark down cells. Keep your code tidy and backed up. Running the cell now. Did you make a mistake? That is okay, debugging is part of learning. Extra tips. Try more datasets, like movies or sports, for more practice. Many data mining concepts also work for text or images. Explore the scikit-learn and pandas documentation for more features. Sharing your findings with friends helps you learn faster. Running the cell now. Challenge exercises. Find a set of 3 items that often appear together. Predict a different item's purchase, such as soda or yogurt. Cluster with 5 or more clusters and describe what you observe. Try visualizing the basket sizes with a histogram. Share your solutions in the comments to help other learners. Running the cell now. Completing the challenges helps you solidify your new skills. Recap. In this lesson, you learned how to explore, clean, and prepare transactional data. How to group transactions into baskets for mining. Basic association rule mining for shopping pattern discovery. Simple classification and clustering from real data. Why testing, visualization, and parameter searching matter. Keep practicing with new data to build your data mining confidence. Running the cell now. Take a moment to reflect. What was the most surprising thing you discovered? Thank you for learning exploratory data mining. If you enjoyed this lesson, please like, subscribe, and share. Check out the next video for deeper dives into machine learning. Happy mining! Running the cell now. What topic do you want to see covered next? Type your ideas in the comments.